The discovery of the most ancient black hole ever confirmed has sent shockwaves through the scientific community, offering tantalizing clues about some of the universe's deepest mysteries. But here's where it gets controversial. This colossal black hole challenges our understanding of how such massive objects could form so soon after the universe began. Could it hold the key to explaining those enigmatic red dots scattered across the early cosmos? Let's dive in and explore what makes this finding so groundbreaking and why it might spark heated debates among astronomers. Imagine a black hole so enormous that its mass equals roughly 300 million times that of our sun. Yet it existed when the universe was merely a cosmic toddler, just 500 million years old, or about 3% of its current age. This behemoth resides in a galaxy named Kuiper's LRDZ9, and its existence defies conventional theories on black hole growth. It's not just big, it's monstrously oversized for its era, making scientists question everything they thought they knew about the early universe. But wait, there's more to this story than one overachieving black hole. Its discovery also sheds light on another puzzling phenomenon: little red dots, LRDs. These celestial oddities are small, intensely bright, and glow with a deep red hue. First spotted by the James Webb Space Telescope, JWST, LRDs appear around 600 million years after the Big Bang, but vanish mysteriously less than a billion years later. What are they? Why do they exist? And why do they disappear? These questions have baffled researchers for years. Now, thanks to JWST's unparalleled ability to peer into the universe's infancy, we're starting to piece together answers. The newly identified black hole at the center of Kuiper's LRDZ9 is classified as an active galactic nucleus, AGN, a type of supermassive black hole that feeds voraciously on surrounding gas and dust. Encased in a fiery cocoon of material, this AGN emits a reddish glow, earning it comparisons to something straight out of science fiction, a black hole star. Sounds wild. Well, the confirmation of a supermassive black hole within Kuiper's LRDZ9 supports the hypothesis that these mysterious red dots harbor similarly gargantuan black holes. Some of these black holes may reach up to 10 million solar masses within their first billion years, an almost incomprehensible scale. To put that into perspective, the supermassive black hole at the heart of our own Milky Way galaxy weighs in at a relatively modest 4 million solar masses. And this is the part most people miss. The black holes inside LRDs aren't just supermassive, they're potentially overmassive. In Kuiper's LRDZ9, the central black hole accounts for nearly half the total stellar mass of its host galaxy. Compare that to nearby galaxies, where central black holes typically represent only about 0.1% of their galaxy's stellar mass. Clearly, something extraordinary was happening in the early universe. Adding to the intrigue, Kuiper's LRDZ9 itself is incredibly compact, measuring no more than 1,140 light-years across. That's comparable in size to the dwarf galaxies orbiting the Milky Way today. Despite its diminutive dimensions, this galaxy hosted a black hole that grew at an astonishing rate, raising new questions about the mechanisms behind such rapid expansion. Researchers propose two possible scenarios for how these black holes became so massive so quickly. One possibility involves a large seed black hole weighing around 10,000 solar masses, growing at the theoretical maximum rate known as the Eddington limit. Alternatively, a smaller seed black hole, perhaps just 100 solar masses, could have grown even faster via the super Eddington rate, fueled by the dense clouds of gas collapsing around it. Either way, the origins of these seeds remain uncertain. They could stem from primordial black holes formed during the Big Bang, the collapse of population 3 stars, the very first luminous objects in the universe, or even chaotic collisions within densely packed star clusters. Pushing the boundaries of modern technology, this research represents the farthest back in time we can currently observe black holes. As Taylor notes, when looking for black holes, this is about as far back as you can practically go. We're really pushing the limits of what current instruments can detect. Ultimately, this study adds compelling evidence that LRDs were fleeting phenomena in the early universe, possibly representing an initial stage in galactic evolution. Could these tiny, brilliant dots have paved the way for galaxies like the Milky Way? Or do they hint at processes we've yet to fully comprehend? This research invites us to reconsider the origins of cosmic structure and maybe even challenge long-held assumptions. What do you think? Do these findings align with your understanding of black holes and galactic formation? Or do they raise more questions than answers? Share your thoughts in the comments below.